Okay, welcome to ECE 590i seminar. Our first speaker today is Shamina, and she received her BS degree in electrical engineering from Washington State University in 2012 and the MS degree from the University of Illinois at Urbana-Champaign in 2014, where she is currently pursuing a PhD degree. Her research currently involves developing data-driven methods for improved control and protection of distributed controllers.
And I forgot to add my advisors, Professor Overby. I don't think I have. Oh, okay, all right. Oh, yes, I do. Okay, awesome, thank you. Okay, well, hi everyone. Again, I'm Shamina, and today I'll be presenting on controllability analysis-based techniques for regaining control in a cyber-adversarial environment. And this is work I did with Kate Davis and Maryam Kazerooni from UIUC, and then Shaharsha Idagani and Saman Zanuz at Rutgers University. So just to start out, of course, distributed controllers are everywhere in the grid and are integral to the function and operation. And examples include protective relays to distributed flexible AC transmission system devices, such as DFACs that are used for power flow control. And however, they are vulnerable to cyber attacks. And as such, we need to develop effective prevention and mitigation methods. And so these controller-based threats can include sending malicious control commands, which could drive the system to an unsafe or unreliable state. And so for an example of an industrial control system attack is in Matrices Water Services in Australia in 2000, where a disgruntled former employee went around with stolen radio equipment to these different distributed sewage equipment sites and issued malicious commands, and then at 46 different sites, and caused about 800,000 liters of sewage to overflow into the town, and thus very detrimental effects. Of course, this isn't the only industrial control system, and in my focus, I'm focusing on distributed controllers in power systems. And so this work is seeking to identify the critical and redundant controllers to maintain system controllability, and also the control support group. So which controllers help each other the most in achieving some control objective. And so just to illustrate what I just said, if we have, say, the 7-bus system, we assume there is a controller on every line. When certain controllers become compromised, as shown in gray, if this research is trying to figure out what is the role of these distributed controllers. Are they critical or redundant to the system control? Or which controllers help each other most so we can mitigate the effects of these compromised controls and also try to regain system controllability? So we're developing an analytical solution to restore the control capability of a system given a controller attack. But this isn't just the results of this research isn't only applicable to malicious control. We could also have benign things like just a controller could fail, or we could have malfunction. And in that case, we still can use these results to maintain or regain control of the system. And so to do this, we examine the system controllability to find those insights about the controller set and how they interact with the system as well as with each other. So to go into background of controllability analysis in power systems, the controllability region of a power system is the subset of the state space where you can use available controls to steer the system from one state to another. And so, which we all learned in 515. And so the controlled power system dynamical equation is shown in equation 1, where x is the n vector of dynamic variables. F of x is a vector consisting primarily of the power flow equations. And the summation of gi of x ui represents the effects of the controls of the system, which is what we're concentrating on. And then those scalars ui represent the system controls, and the system state space, xi, is an open subset of the n-dimensional Euclidean space. And so if we have this x of S0 u t, where S0 is the initial state, represents the system movement, where u is the control and t is our time, 0 to infinity. And so for the controllability region, It's any pair of states, S1 and S2, that satisfy the equation presented in 2. So within that controllability region, there exists a control U that in the finite time t can steer the system from S1 to S2. And so all those states for which this condition is true create the controllability region. And that controllability region is called Z, which is the subset of the entire state space. And so there's been a lot of work done in controllability analysis and nonlinear and linear methods, as most of our systems that we study are nonlinear. There's been nonlinear controllability analysis work, but it's very complex and is not tractable at the moment, but some of our research is looking into that. But most of the methods developed are linear, and a lot of them in power systems use modal analysis. And a classic linear method is the PBH eigenvector tests that check the rank condition of, say, our controllability matrix. But these tests only provide yes or no answers. So yes, the system is controllable. No, it is not. And what we're seeking is a more detailed result, specifically the role of each of the distributed controllers and how they contribute to that system controllability. And so our approach has 2 aims. So the first aim is that we identify the line flow groups, so the sets of transmission lines that can be controlled independently, and the control support groups, so the controller devices that can provide that control. And so in terms of that control dynamical equation I gave earlier, we want to decompose that effects of control GI of X UI summation into groups. So for example, we have 3 groups here, group 1, 2, and 3, and have the list of controllers that are within the control support groups help each other the most in achieving some objective, whether it be controlling a specific line flow group. And then secondly, we would like to obtain the set of critical controllers and redundant controllers. And so in this case, the critical controllers are the minimal set of devices required to maintain the system controllability. And the redundant controllers are the devices that can be removed without affecting the system controllability. And so this is again shown in that control dynamical equation where we have 2 sets shown in 4, where we have all the critical controllers shown in the first line and all the redundant to the total number of redundant controllers, or TR. So to perform our analysis, we use sensitivity matrices. And so the appropriate sensitivity matrix must be used depending on your controller and the control objective that you are studying. And so, for example, if we had a SVC or static VAR compensator system that we're using for voltage regulation, for example image here, we want a sensitivity matrix that captures the control, so the reactance or capacitance, depending on if we're lowering or raising the system voltage, and the controlled quantity, the objective, the transmission bus voltages.
Where's that at?
I'm not sure. I'll look it up though. And then, so for our case, to aid in my explanation here, I'm going to use an example of DFAX controllers, where these controllers act as a synchronous voltage source in series with the line, and changing the line's effective impedance and thus its power flow. And so in this case, the control is the effective impedance, and the controlled quantity is the line power flow. And so I'm kind of skipping all the details here, but we calculated a sensitivity matrix that considers the total sensitivities of the power flows to the impedance as a sum of the indirect and direct sensitivities. And so now that we have this sensitivity matrix, we're going to cluster and factorize upon it. And this is just an example of some DFAX devices on our favorite 7-bus system. So for the identifying the sets of the line flow groups and the control support groups, we're going to cluster on the rows of the sensitivity matrix. And so identifying those line flow groups, in the case of DFAX controllers, which are trying to control line power flow, is crucial in the comprehensive power flow control. And so within each set of these line flow groups, we have a set of transmission lines that can be independently controlled. And so within the group, they are highly coupled. And so changing or controlling any line within that group will predictably impact all the others in that group in a predictable fashion. And each of these clusters are going to be highly independent of each other. And so to illustrate that, in part B of the figure, we show if we had the rows of the sensitivity matrix, so different power flows, when they're highly coupled, the vectors are aligned and the angle between them is 0. However, when they are completely decoupled, they will be orthogonal to each other as shown in A. And so using that information, that we know that when they're completely coupled, the angle is going to be 0. And then when they're completely decoupled, the vectors are orthogonal. We're going to use that information to create our distance matrix from the sensitivity matrix to cluster upon. And so for that, we find the cosine of the angles between the vectors of the sensitivity matrix, and we call that the coupling index, CI, defined in equation 5. And so when they're completely coupled, the CI has an absolute value of 1, and the angle between the vectors is 0, so as shown in the figure before. And when they're completely decoupled, the CI is 0, and the vectors are orthogonal independent. And of course, in the distance matrix, they're going to range from 0 to 1, and we want to cluster the most highly coupled transmission lines together. And so each cluster will be independent and decoupled from the other sets. But within each cluster, the line flows of those transmission lines are coupled and dependent on one another. And so once we have that distance matrix, we clustered them using the hierarchical agglomerative clustering. And for that, you have to specify, so it creates a cluster tree or dendrogram. And so you either specify a cutoff value, or you specify a maximum cluster number to form the resultant clusters. And so to determine, we use the maximum cluster number, and to determine a data-dependent maximum cluster number, because we want the most highly coupled lines to be within each line flow group, we developed an algorithm that used singular value decomposition, SVD, and optimal hard threshold to determine the most significant singular values, using the interpretation that the most significant or largest will represent the most significant groups present within the data, which is our sensitivity matrix. And so we use that as the initial guess for the number of clusters. And so this just kind of summarizes that process that I'm not going into too much detail here. So now that we have the line flow groups, as well as the controllers that work, the control support groups, so the controllers that help each other most to control those groups, we look at applying the factorization method onto the sensitivity matrix to find the critical and redundant controller sets. And so in this case, the protection of the critical controllers would be essential in maintaining the system controllability. And if a redundant controller is compromised, we can determine how to recover any malicious effects on the system using its support group, because we know those controllers within its support group are going to be the most effective. And so in this figure, I'm just showing that when we have a critical controller on the right, gray, compromise is going to be a different situation than when we have a redundant controller compromise, shown on the left gray circle. And so this decomposition requires examining the coupling of the columns of the sensitivity matrix. And just to remind, we're still using our defects example, that the rows correspond to the controllers, the defects controllers, and the columns now correspond to the real power flows that are going to be controlled. And so essentially for this decomposition, the idea is that we're going to perform a change of basis to obtain a mapping from the control devices to its equivalent states. So to control the equivalent line flows. And so this is based on LU decomposition, where A double prime is actually our sensitivity matrix. And what we find is we get this new basis that has the structure shown in equation 8. And so each row in that transformed matrix, shown in equation 8 again, will correspond to a respective controller. And so the rows of IN correspond to the critical controls that are sufficient to assume independent controllability of the system. And so the controls corresponding to a row in IN is critical, since the equivalent line flow on the column has no non-zero entry besides for that control, and so we can only control that equivalent line flow with that control, and thus is critical for the system controllability. Whereas the rows of R correspond to redundant controls, where we have multiple controllers that can control that equivalent line flow. And so this is how we get our critical and redundant controller sets. So for our evaluation, so we'll go to the very familiar 7-bus system with 5 generators and 11 lines. And again, the controllers are going to be those DFAC devices whose control objective is to change the line flows by changing the effective impedance. And so by applying our, calculating the sensitivity matrix, the total sensitivity matrix, and applying our clustering and factorization techniques, we get the results shown in both of these tables. We have 6 clusters of different transmission lines, shown as L1 through L11. And then we have the resultant critical and redundant controller sets, where our critical controls are the controllers on line 2, 3, 4, 5, 7, and 8. And I didn't mention, but we assumed that there was a controller on every line in the system, but that is not, that's just for simplicity, but you can change that. However many controllers have, however many lines you're controlling, it just depends on how you construct the sensitivity matrix. And finally, this is shown in that dynamical equation again with the 6 different clustered groups and our critical and redundant controllers labeled. This is just illustrated again with the clustered lines labeled and colored, and the critical and redundant controllers also labeled. So now that we have this information, we can use this insight for developing strategies to regain or maintain control given we have some controller attack or failure of certain controllers. So if we only have redundant controllers compromised for this first situation, so for example, if we had the controllers on line 1 and 9, as shown in gray in the figure, compromised, we know that the critical controllers in group 1, since L1 was in group 1, all the rest of the controllers within that control support group are going to be the most effective in trying to mitigate any adverse actions that compromised controllers try to take. The L9 controller is independently controlled, meaning that it doesn't have a control support group. And knowing that, we know that we need to use the coordinated efforts of multiple uncompromised controls to mitigate any adverse actions that is taking. And finally, since no critical controllers have been compromised, we still maintain the full system control. So we can treat this with a different degree of emergency. However, when we have critical controllers compromised, so for example, the controllers on L2, 5, and 8, as shown in gray, we know that L1 and L6 are going to, of the cluster group 1, are going to be most effective in trying to mitigate any actions from the compromised 2 and 8 controllers. And again, controller on L5 has no other controls in its support group. We're going to need a coordinated effort. But in this case, we do not have full system controllability since we have critical controllers compromised. And we need serious emergency efforts to regain that control. And that's the same case when we have both critical and redundant controllers compromised. We're going to utilize all the system uncompromised system controls to try to regain full controllability. But again, we'll be using the grouping information, those line flow groups or control support groups, to be the most effective in that effort. And from the decomposed critical and redundant controller sets, we know we need to try to restore the critical controllers first. And so as we demonstrated, this analysis provides that insight of which of the distributed controller set are critical and redundant. And as well as, so we can redirect our efforts to first restore critical controllers and know the degree of emergency we have. And also utilize the most effective controllers to mitigate any adverse effects that the compromised controls are trying to take. And additionally, having that grouping information also aids in controller placement when you're trying to fulfill certain control objectives. In this case, we did not consider, so when we had those compromised controls, say we had the redundant compromised controls, but we said full system control is still maintained. But we need to consider also the adverse actions, the extent of malicious activity those controllers can do, and see how that impacts the system controllability, because we could have a set of redundant controllers doing enough malicious actions that system control can be lost. And that's the next step that we're doing in this research. So yeah, thank you. Questions?
That's a nice presentation.
Thank you.
How would you say this scales as you increase the size of the
System? So I didn't show this here, but I did do a 118 bus case that has 189 lines. And I think it did scale well. It did take a little longer, but it was still within a few seconds that I was able to do the analysis. Yeah, but I mean, it is going to be slower as you cluster, like, you know, bigger matrices and everything.
You know how your clustering algorithm scales?
I'm not exactly sure, like, on the computational order. Yeah, but I'll definitely look into that. Yeah, thank you. All right, thank you. Yeah, thank you. Oh, let me also give you this. Thank you.
Our second speaker today is Maryam Kazerooni, and she received her BS degree in 2010 from Sharif University of Technology, Iran, and her MS degree in 2012 from the University of Windsor, Canada, both in electrical engineering. She is currently a PhD candidate in electrical engineering at the University of Illinois, Urbana-Champaign. Her current research interests include power system reliability, state estimation, and geomagnetic disturbance analysis.
Yes.
No, I think that's for PDF.
It's what?
If you go to maybe in view. No, not there. Okay. Thank you. Hi everyone, again I'm Maryam, and today I'm going to talk about mitigation of geomagnetic disturbances using corrective control actions. So let me start with an introduction on what is geomagnetic induced currents shorting gigs. The activities at the surface of the sun disturb the magnetic field around the Earth's surface. By Faraday's law, these magnetic field disturbances induce electric field on a transmission line, and that electric field induces a quasi-DC current on the lines, which we refer to as geomagnetically induced currents, or gigs. Gigs have negative impacts on the power system. For one thing, they increase the reactive power loss on transformers, and also they increase harmonics. In the worst case, they can even cause a blackout, like we had the 1989 Quebec blackout. Motivated by these negative impacts, we want to come up with some corrective control actions to minimize the impacts and protect the network from GMDs. So in this presentation, I am first going to talk about how we calculate the gig-saturated reactive power losses in transformers. Then I will present the algorithm that we developed to minimize the losses on transformers. And I will present some numerical results for different systems. In the second part of the presentation, we use a second approach for minimizing the losses, that is using the transformer neutral capacitors, and I will also present some results for that. When we have some gigs passing through a transformer, we model, it increases the reactive power loss. We model this additional reactive power loss by a DC current source on this parallel branch that you see. And the amount of the DC current is proportional to the effective gigs. And I should say that the effective gig is a function of the gigs passing through the high side and low side of a transformer, and also the transformer turn ratio. Now, to calculate the effective gigs, we need to have some parameters. First, we need the electric field that is induced on the power system. Also, we need these three matrices that you see. One is phi, which captures the transformer configuration, like if it's delta Y connected, or if it's auto transformer, the transformer turn ratio, and also the resistance of a transformer. We also have this G matrix that captures the topology and resistances of the whole network. It is very similar to the real part of the admittance matrix. The Y bus, sorry. And also we have H that captures the orientation and also the length of the lines. So with this, we can calculate the effective current on the transformer, and according to that, also the gig-saturated losses. So now the purpose of the algorithm that we developed is to minimize the total losses in the system. So for a network, we want to use line switching to minimize the losses. And the question is, what are the best lines to select for opening so the losses are minimized? We use a sensitivity analysis to find the best lines. So we define, so similar to line outage distribution factors or LODFs that are typically used for AC analysis, we define a transformer line outage distribution factor, or short in TLODFs, and we use that as the criteria for line selection. So TLODF, as you can see, is in this example, is the amount of losses reduction that you get, say, in transformer I, if you open line J. And then with this definition, you can create the TLODF matrix where each row will correspond to each transformer, and then the columns will correspond to the lines. So basically, to calculate, for example, the first column of this matrix, you open the first line, then you look at the amount of reduction that you get in each individual transformer, and that will give you the first column. So once you have the TLODF matrix, we use an iterative algorithm to select the lines that we want to open. In the first iteration, we start with the TLODF matrix. We take the sum over the rows of the matrix to give us the total reduction that you get over all the transformers. Then you sort this sum, and then the first line in the sorted list will be the best line to open. Then in the second iteration, now you already have opened one line, so you have to calculate the TLODF for this new system with one less line, and then you repeat the process. You take the sum, you sort them, and then the first line in the sorted list is the best line to open. And you keep doing that until you reduce the losses to some desired amount. Now, the problem with this approach is that at each iteration, you have to calculate the TLODF, and that is computationally expensive. So to address this issue, we came up with a faster version of the algorithm. And in this faster method, So the first iteration is the same. You calculate the TLODF, you take the sum and you sort it, and then the first line in the sorted list is the first line that you open. But what another thing that you do is that you look at the first, say 5% of the lines in the sorted list, and you take them as your critical lines. So in the next iterations, you only focus on the critical lines. So for example, in the second iteration, you calculate the TLODF only for that, for example, 5% of the lines. So the computation is much less this time. And then you select the best line among the critical lines. And what we did for this algorithm is that, for example, you do the first 30 or 40 iterations like that, but after that you go back to the big matrix, like at the youth iteration, and you recalculate the full matrix to update the critical lines. So in this algorithm, we have two parameters that we need to specify. One is how many critical lines we want to select, and also after how many iterations, it's good to go back and calculate the TLODF matrix. And of course, these parameters will determine the computational complexity of the algorithm. So whenever it is like larger, then you have better accuracy, but then more running time.
So Maryam, if you knew what lines you might likely open, because you've done this before.
Yeah.
L's pretty little, or could be pretty little, right? Lines.
The number of lines that you open?
You don't have to consider every line because you know you're not going to open every line.
Yeah.
So the little dinky ones you wouldn't care about, so it's just a few. You could actually just have a pretty small number of L's.
So like, for example, for the 2000 bus, you have like 3000 lines. And then out of these, you can like open up to like 50 lines, and you can still reduce the losses. So the number isn't that small.
But it's not that big.
Yeah.
Once
so
you've done it a few times, you know which one.
Yeah, that's true. Yeah, maybe, so that would be like maybe finding the critical lines for just once, and then maybe you're suggesting that we don't need to update the critical lines again, right?
Yeah,
Okay.
You can learn.
Yeah, I have like the results that shows like how much it diverges. If you don't update at all, it's not much. Yeah, you're right. Yeah, like we end up like updating after 40 or 60 iterations. So maybe just 2 times in total. Yeah. Okay, I guess. Okay. So with this line switching algorithm, we have to be careful that when we open a line, even though we are reducing the losses, the gig-saturated losses, but we are also changing the topology of the system, so that will also change the AC flows on the system. So we need to be careful that by switching these lines, we would still get some agreeable AC solution. To capture that, we came up with some very basic heuristics for incorporating the AC security measures. So one is that we want to select a line that will give us an AC solution. For that, what we do, like in the sorted list, before we would just select the first line, but now what we do is that for each line that we have as candidate, first we check if the Y-bus is not ill conditions, we select it. If not, we move to the second line in the sorted list, and then we keep doing that until we have a line that gives us a Y-bus full rank matrix. And that is not computationally expensive, so it doesn't add like complexity, so it's good. The second heuristic that we use is that before we would only look at the TLODFs for our selection, but now we use this selection index. So it's a combination of TLODFs and also the AC line flows. And you see that the AC line flows are in the denominator. So you end up selecting the line that reduces the losses the more, and also it has lower AC flows on them. And this is just through experimental simulation results. We saw that this will give us a better solution, as I will present later. So we applied the algorithm to three systems, one a small size, a medium size, and a larger system. So this is the 20 bus system that we start with. We enforce an electric field with 8 volt per kilometer, and then the direction. So we select a direction that gives us the highest gigs. So the system is most vulnerable to this direction. Yeah. So on the table on the top, you see the results that we get from the iterative algorithm. So in each iteration, you keep opening more lines, and you see that as you open more lines, the losses in the system decreases. And now we compare this solution with the exhaustive search, just so we know how good the algorithm is. That would be the second table. So for example, we have the exhaustive search when the number of lines is 2. When the exhaustive search is basically, you look at all the combinations of selecting 2 lines from all the lines that you have. And you see that the solution that we get, that would be in red, is the second best solution. So it's not optimal, but it's still good enough. And then the advantage is that the running time is much, much better. So for example, for 3 lines, you see that the running time for the exhaustive search is 21 seconds, whereas the algorithm is only 0.3 seconds. And also the losses that you get, for example, for the exhaustive search is 12.1. But then our algorithm is like 12.3. So not the same, but this is still like very close. The next system is the 150 bus system. This is a synthetic case of the Tennessee region using the load and generation public data, and based on some power system statistical analysis. We use the same magnitude electric field, and again in the maximum direction for this system. And here are the results for our algorithm. So we consider 2 scenarios. In the first one, we only use the TLODFs as the selection criteria. That would be the blue line in both figures. And in the second approach, we use a combination of TLODFs and the AC line flows as our selection criteria. On the left, you see the reactive power loss, the total reactive power loss as a function of the number of lines that you open. And on the right, you see the average bus voltages. Now, if you look at, for example, the figure on the left, you see that in each iteration, when you only look at consider TLODF, you end up getting a lower losses, which is good. But then if you look at the voltage, you see that the one that only considers TLODF has a much lower voltage. So the voltage profile isn't very good. Also, one thing to mention is that you see that the blue line, you only have it up to the 7th iteration, and it's not there anymore. That's because beyond that point, we couldn't find any more line to open that will still give us an AC power flow solution. But then for the one that has the combination of both, you are able to proceed to up to 22 lines opening, and you still get a power flow solution. And here's the result for the individual transformer. So what is the losses in each individual transformer? The blue is when we don't have any action, and then the red is after you apply the line switching algorithm. And you can see that for most of the transformers, you end up decreasing the losses significantly.
How many lines did you switch?
So this would be this one, like 22 lines. So next we move to the larger case. This is a 2,000 bus system. Again, it's synthetic case of the Texas region using the public load and generation data, and then some power system and statistical analysis. We use the same magnitude electric field, and then again in the maximum direction. So yeah, this is the figure that I was mentioning. So here just to give us some idea what should be the update frequency for our algorithm, we ran 2 scenarios. The first one, which is the red curve in the figure, is where you update the TLODF each time. And then so it's like the full calculation. And then the green one is where you don't update the TLODF at all. You just calculate it once, and then you select the 200 lines that are the best, and you just keep using those. And you see that you get almost the same results for up to the 60th iteration, and that's when that they start diverging. But even then, it's not that much. So it's a trade-off. Once you update more, you just have like, you reduce the losses more, but then you have to like have a larger running time. And so now we did the same experiment for different values of that update frequency and also the number of critical lines that we have. So here in this table, the first row is when you don't have any action. The total loss is 129 per unit. Scenario A is the full calculation when you are updating the TLODF every time. With that, you reduce the losses to 78, but the running time is 3,000 seconds, which is really high. But then, for example, if you look at the last row, that is scenario E, the update frequency is 40, the number of critical lines is 100, and with that one, you get just in 100 seconds, you can reduce the losses to 80. It's not as low as the full calculation, but if you consider the running time, it makes sense to just use the faster version.
How many lines did you open here?
So this one, I opened 120, but I think you could open more and you still get AC power flow solution.
Really?
Yeah, it has like 3,000 lines, so.
That's 120.
Yeah. Yeah. And okay, I'll go through this fast. So now the second approach that we use is that we can put some blocking devices on the transformer neutral to block the gig that is passing through the transformer. This way you won't have any loss on that particular transformer, and also you get to redirect the flows on other lines. Now the question is that say you have this option of blocking all the transformers. What are the best transformers to block to minimize the losses as much as possible? And you don't want to block all the transformers because it causes like isolation issues if you are not grounding one substation. So now to find the best transformers to block, we use the same approach, sensitivity analysis. This time we have the transformer blocking distribution factors, or TBDF. That is the effect of like how much the losses in transformer I changes if you block transformer J. So it's very similar to the TLODF. So again, with this definition, you can create the TBDF matrix. It would be, the rows will be the transformers that you're looking at its losses, and then the columns are the transformers that you're blocking. And then the algorithm is, this one's not iterative. You just take the sum of the rows, you sort them, and then you just start with the top of the list. You keep blocking the transformers until the amount of losses that you get is like it's equal to the amount that you want, and that's when you stop. And here's the solution for the 150, the simulation results for the 150 bus system. On the left, you have the reactive power loss as you employ more blocking devices, and on the right you have the average voltage. And yeah, for this, using blocking devices is much more effective than opening a line. Like with employing 25 blocking devices, you can reduce the losses to almost zero, and you keep improving the voltage profile. That's because with opening a line, you are changing the AC flows, but with blocking a transformer, you don't affect the AC solution. But then again, blocking devices are more costly, so you have that limitation. And yeah, to conclude, we presented a technique to find the best lines to open to minimize the losses, the gig saturated losses in transformers during GMDs. And the algorithm includes some AC aspects of the power system. Also, we evaluated the performance using systems of different sizes. We also looked at how to use transformer and neutral capacitor as the remedial action to mitigate the GMDs. So yeah, that's all. Yeah, and I can, yeah, if there's any question, I'd be happy to ask. Sure.
So that's a nice presentation.
Thank you.
Probably the most powerful aspect of this is just opening a few lines to block the GICs or to modify the GICs on a particular number of transformers. Because if you know, what you should convey in your paper is that, look, we can open 100 lines, but we probably don't want to do that.
Yeah.
The algorithm can handle that, but we probably want to block them on some transformers that we're concerned about.
Yeah, and especially with like the Texas, I didn't show the voltage. The voltage profile isn't good when you open 120 line. You still get a solution, but it's not a good one.
Well, right. I mean,
Yeah.
if anybody says you take a 2,000 bus system and you take out 120 lines,
Yeah.
you know, it's
Yeah.
going to cause trouble.
Yeah, yeah, it would be better to just focus on maybe the transformers that have the highest losses and then try to, yeah, put a limit on that. Yeah, sure.
If you look back to the slide where you, the last, where you showed the,
This one? Yeah.
so you updated in A, you only updated the TLODF once?
No, every iteration.
Every iteration?
Yes.
And then on E, it was every 40 iterations?
Yes, that's true.
So, and the runtime, there was 3,000 seconds.
Yeah. So yeah, scenario E, the running time is almost like 3% of the full search.
So how did you determine the update frequency? Was that just arbitrary?
Yeah, basically from this figure, like you see that if you don't update, it starts diverging from 60. So I actually put like 60 too. And it's a matter of like the computation complexity. You can put anything, but then the running time will be more or the accuracy will be worse. It's a trade-off.
When you're disconnecting lines, you're both trying to redistribute where these sticks are going, which transformers. Are you also trying to take out lines that are most coupled to the induced field? Is that your role? Take out the lines that are most like in and out?
Actually, that could be another criteria. So as of now, we only look at like that sensitivity matrix. We just say if you open this line, it'll change the losses in the transformers this much, and we use just that. But yeah, maybe one would be like how much couple, like based on the direction of the electric field, which line has like the highest gigs or something like that.
But you'd think they'd be coupled.
Yeah.
That you're taking out the lines, probably. They could
Yeah,
be
it'll show up in the,
field.
yeah, it'll show up in the, yeah. Yeah, but like we don't directly like present it like that, yeah. Yeah.
So I got another question. With the TLODS, if you computed them once for the system, when you open a line, do you know the sensitivity or how sensitive the system is to change? In other words, once you open a line, would you really have to recompute the TLODS for the entire system? I mean, considering the fact that if you compute the TLODS for the entire system in the beginning, the topology, the physical topology is not changing much. So even though you open up a line, the relative TLODS on all the other lines should change.
But not that much.
In a relative manner, right? So
yeah. Yeah, yeah, it would be again like this scenario B that you don't update it at all, and then the result is like, it would be here, like you don't update at all. So you get like this much losses, which is still reasonable. Yeah, you're right. We could just use that. So yeah, instead of getting 78, you get like 90 I mean, yeah, it's like, again, it's trade-off. Like, it won't be as good as like, for example, scenario A, or it won't be as good as scenario E or scenario A, but then the running time will be less. You just need to like figure out like the trade-off and what you want, like based on the size of the system, the time that you can spend on like just getting the solution. Yeah. 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 Thank you.